In this lecture, we're going to continue our part 2 of substitution reactions setting the scene. So what we've discussed up until now is this acronym SCENE, which is to help us to remember the different components that are important in deciding between an SN1 reaction versus an SN2 reaction. And we've looked at the S, which stands for sterics, the C, the carbocation, and the E, the electrophile. And all three of those are kind of interconnected with each other. And we need to consider them all in terms of the electrophile of the reaction to decide whether we're using an SN1 or SN2 reaction. In this lecture, I want to look at the nucleophile and the environment. So let's look at that. So the first thing is the nucleophile. Now, the nucleophile is normally quite easy to identify. We've had quite a bit of experience with that. We're looking for lone pairs or negative charges, something like that. But typically, it's actually quite easy to use the nucleophile as a way to kind of help us decide between an SN1 and SN2 reaction. The first thing is that an SN1 reaction will typically have bad or weak nucleophiles. If we are saying that a nucleophile is bad or weak, what do we mean by that? Well, possibly like the most important example is or are the alcohols. Alcohols are not great nucleophiles at all. They're examples of water, organic versions of water, and the lone pair of electrons on an alcohol is really not good as a nucleophile. And so we would have to have a very strong electrophile to want this to react with. And you can compare that information if you go back to the reactions on carbonyls. For instance, an alcohol would react very rapidly with an acid chloride, which is a very reactive electrophile. So if we see an alcohol as a nucleophile, just as it is, it really is not a good nucleophile at all. Linked to that are the, but not as much, are the thiols, which are directly below, so sulfur is directly below oxygen in the periodic table. Now, I put this one here just again also quite cautiously because sulfur, because it is low on the periodic table, it's a much larger atom and it's using these lone pairs are sitting in higher orbitals, and so the lone pairs on sulfur are more nucleophilic than oxygen. And so sulfur is more nucleophilic than oxygen, but typically a neutral thiol is not something that would be pushing us towards thinking about SN2, probably more SN1. But again, we have to look at the whole picture. So we just have to look at that when we do some of the examples. And the other example of bad nucleophiles are our halides. So say a Br minus as an example. So these would be examples of not great nucleophiles. Again, our decision between SN1 and SN2 isn't based on just one thing. We do need to look at the whole picture, the whole scene. So it's not just an SN1. With SN2 reactions, it's really essentially all the rest. So here we're looking at typically strong nucleophiles. So examples of this are things like, a great one for an SN2 reaction would be a nitrile. We are also looking at essentially our amines. Amines are excellent at doing substitution reactions. It actually becomes a bit of a problem. We'll deal with that in a future lecture, I think. But we would also have things like what is below nitrogen is phosphorus. So any kind of phosphorus or phosphine that has a lone pair of electrons on a phosphorus with a lone pair is an absolutely excellent nucleophile for doing substitution reactions. And then really, because we're looking at strong nucleophiles, so nitrogen's lone pair is great compared to oxygen, which is not that great. So nitrogen is great. However, we can make oxygen and sulfur better by removing that proton. So we get the O minus. So whenever we have something like an O minus, that's quite excellent. That's strong nucleophile now, and our S minus. So an S minus is also strong. I'm going to say a little bit of a proviso here. We need to be very careful, particularly when we start going to an O minus like this. we start moving into the territory of not a nucleophile but a base, and that's going to become important a bit later on. But nevertheless, this kind of gives a bit of an overview of the types of nucleophiles to look at. If you want to remember this, you could have some sort of acronym would be bad 1 and 2 strong. So that might sort of mnemonic or whatever might help you remember these two things that we're looking for in terms of nucleophiles. With that in mind, let's just have a look at an example just to see how we would apply this, also including some of the other ones before we look at the environment. I've got here two reactions on this molecule. It's a functionalized aromatic. Basically looks like benzyl alcohol, but with the bromine over there. I just put the bromine there for it's fairly random, but just to show you some other functional group here. And let's look at the top reaction over here and consider our the acronym scene. Let's just look at the different things that are happening over here. So the first thing that we need to identify when we look at something like this are our potential nucleophile and electrophile. So on this molecule over here, we obviously have lone pairs around the bromine, which are potentially nucleophilic, and we've got lone pairs on the oxygen, which are potentially nucleophilic. And that really is the only nucleophilic, the best nucleophilic part will be the lone pairs on the oxygen, far more so than lone pairs on bromine. So that'll be our nucleophilic part. There is no leaving group on this molecule over here. One of the reasons I put the bromine there was to remember that bromine on an aromatic ring, absolutely not a leaving group. So that cannot take part in a substitution reaction, and so we do not need to consider that. The leaving group, though, of course, is very clear. Over here, we've got this iodine over there. So when we look at that, we need to ask ourselves the questions. In terms of sterics is absolutely very small here. The leaving group is on a methyl group. It's one of the least sterically hindered thing at all. So over here, we are definitely moving towards the SN2, which I normally put at the bottom. The carbocation that forms over here is just non-existent. You would not want to form a methyl with a carbocation on it with the leaving group. So this absolutely is, again, kind of pushing towards, we would definitely want to have this as a on a SN2 type reaction. And all of this ties in with the electrophile as well. The electrophile, we've got a good leaving group over there, and that would be fine for both of those reactions over there. So that's a kind of balances off, and it really makes no difference. Now we need to look at the nucleophile, and this example is actually one that's going to lead into our next thing when we start looking at E. We haven't discussed the environment yet, but we need to look at that. And at the moment, the nucleophile as an alcohol over here is really, really bad. And what's actually happening is the nucleophile is really, over this point over here, definitely pushing it towards what would look like an SN1 reaction, because alcohols are not good nucleophiles. However, and this is where we'll see this next part, which I'll introduce after these two examples, is the environment is an important thing to look at, because what we have here is a very strong base in the form of sodium hydride. And sodium hydride is going to absolutely react with this alcohol over there. So the sodium hydride will deprotonate that, and actually what's going to happen is we're going to generate the alkoxide before the reaction occurs, and so we're going to get an O- like that, which is then going to want to react with the methyl iodide. And what's happened is that the nucleophile isn't really, at first glance, this nucleophile looks like it's an OH, but actually it's not that at all. And this is definitely going to be an SN2 reaction where the nucleophile adds and we kick out the leaving group like that. So we're generating this new, much stronger nucleophile, definitely pushing towards an SN2 type reaction. We've got a great electrophile for an SN2 reaction. It's small, good leaving group, no carbocation possibility of being formed, and so we're going to kick that out and we'll form our product, which is the methyl ether, which I'll draw out. Okay, so our first reaction over here, which we worked out, is going to be an SN2 SN2 reaction, without a doubt. Now, but what about this one over here? So this reaction over here, at first glance, looks very similar. So we need to set the scene again over here and decide what are we going to do over here. So in this case over here, the first question is, do we have any steric hindrance or whatever? So we need to, of course, I didn't identify. We've got a leaving group over here. Not the best leaving group, but it is a reasonable leaving group. So in terms of sterics, we are not anywhere near concerned about sterics. So it's certainly looking like an SN2 from a sterics point of view. The carbocation, though, is the interesting thing. And that is because if this leaves over here, we've got lone pair of electrons next door to this carbocation, which can resonance stabilize that carbocation. And that's quite an important feature over there, which means that the carbocation, if this had to be an SN1 reaction, the carbocation is absolutely a great one in terms of an SN1 type of reaction. In terms of the electrophile, obviously the sterics and carbocation are connected to the electrophile. The last thing we need to look at with the electrophile is this leaving group. And the leaving group over here is as reasonable. There really isn't any too much of a difference over there. In fact, often there's not really a difference with an electrophile. We don't even have to consider it once we've done these two things to really kind of consider that, because they are often just equally connected to each other. Not always, but often. The next question, though, now is the nucleophile. The nucleophile that we have is an alcohol, and this is where we need to know our acids and bases very carefully, because the alcohol is not a good nucleophile, but triethylamine, which has the protonated form, is a pKa of 11, and this alcohol over here has a pKa of 16. Triethylamine cannot deprotonate this OH over here. So this mechanism cannot occur in the way that this has happened over here, where we're generating an O minus. And so we've got an alcohol, which is a terrible nucleophile. And so we are very much on the side of an SN1 type of reaction that's occurring over here. The last thing is the environment, which we're going to deal with, and that's, we'll talk about all the things to look at. One aspect that we've been looking at over here is what reagents are available. Are we working with acids and bases? And in this case over here, we've got a base here, but the base is not strong enough to deprotonate. And so this reaction must go via an SN1 reaction. And so if we need to do the mechanism, it's going to pop off like that. So we're going to get this. By the way, this reagent that we're looking at over here is a common protecting group for alcohols. I'll draw it out now. And what we can see then is, we'll draw out the alcohol this way. And what we can see now is that this proton on an oxygen, now it's an oxonium, that proton is very acidic and easy to remove, and our base can come and pick that up. Just interesting, notice that this reaction, which I said is actually quite common, notice that this functional group that's been formed over there is actually an acetal, a carbon with two oxygens on it. So this protecting group can actually be taken off. You can reveal this alcohol, go back to the starting material if you treat this with acid. And that's just a side note for this. The last thing we need to look at in terms of setting the scene and looking at this whole big picture of substitution reactions is to look at the environment that the reaction is taking place in. And to look at this, there are actually four things that we need to look at, which are really helpful. So the first thing is solvent. The next thing is temperature. And then the last two things that I like to just consider are whether we're doing this reaction in acid or base. And that can help us. So this is another acronym. The acronym will be STAB, S-T-A-B. So take a stab at this. Might be better than, stabbing someone. if we look at all of these are really going to help us just decide whether we're dealing with an SN1 or an SN2 reaction. So how does this help us? Okay, so let's look at the solvent first. So with solvents, SN1 reactions are typically in polar protic solvents. Examples of polar and protic solvents are simply things like water, alcohols like ethanol, and another classic example of a polar protic solvent is acetic acid. So SN1 reactions, if we're dealing in these types of solvents, then they are typically going to be in SN1. Now, the question, of course, is why is that? Why do we need polar and protic solvents? The reason is that in an SN1 reaction, remember that the starting point is the formation of a carbocation, effectively. If I go back to the previous example, we saw over here, this was the resonance stabled ion. There would have also been a Cl minus that's present. Now, that is a very polar environment, and we need something to stabilize those two charges. Otherwise, they're just going to want to come back together again. So solvents that are very polar and they are protic, they're able to kind of help separate out those two charges and allow them to do that. So let's write that down. SN2 reactions are typically in aprotic solvents, but here it's not as clear cut. So aprotic is typically one of the things, generally speaking, less polar, but that's not always 100% true. So typical examples of SN2 reactions, it's quite a lot of solvents really. So acetone is really good, but acetone is also quite polar. It's just not protic in any significant way. DMF is actually quite polar, but it's aprotic and quite good. DMSO is also a good. It's more polar, so it's not really less polar, and it is aprotic. And then other solvents I've certainly done reactions in that work quite nicely is just dichloromethane and even THF. We can do reactions in there. So these are the aprotic solvents. Typically less polar is better, but sometimes you have to play around with the conditions a bit with that. Why aprotic? Aprotic is because typically SN2 reactions involve using a good nucleophile, and nucleophiles tend to be sort of basic. They might have a negative charge, and a protic solvent is just going to go and protonate that, so it wouldn't react. So SN2 reactions often need to have that sort of strong base present, and so a protic solvent is not going, or a protic solvent would be a problem. And then less polar solvents has to do with stabilizing the transition state. Why is that so? Typically, when you've got a transition state in an SN2 reaction, what's happening is you have this carbon, you'll have some, so let's just got the two hydrogens over there. And so we've got a leaving group and we've got this nucleophile that's coming in. And the nucleophile will be sort of charged and the leaving group will be charged, but actually overall, initially, as this is happening, it's actually a relatively non-polar environment. So this part is kind of flat. The nucleophile coming in and the leaving group leaving are both negatively charged, but they're kind of in tension between each other. So that transition state is sort of stabilized by a or a slightly less polar solvent. Like I said, that's not always the case. There's a couple of other things that will sort of determine what solvent you want to do over here. But the most important thing with an SN2 reaction really is the fact that it shouldn't be a protic solvent. That's typically a very bad choice. Whereas SN1, it's very clear that a polar and a protic solvent are quite important for pushing those two. All right, then in terms of temperature, this is actually quite an easy one. SN1 reactions are typically done at high temperatures. SN2 might be, but SN1 is almost always at a high temperature. Again, it's not an overall deciding factor. Let me just go back. This reaction over here is not done at a high temperature. We can do this one at room temperature because the carbocation is stabilized. But SN1 reactions typically have to generate a carbocation, and in generating that, we've got to break a bond. Breaking that bond is difficult, so we often have to put heat in, energy, in order to do that. So, yeah. How do we know that we're doing something at a high temp? A typical example is look for the symbol, which the delta symbol over here, which means reflux. We're doing the reaction, we're heating this reaction, and that's usually quite a good indicator that we're probably moving towards more like a substitution. Again, there's never really just one thing when we're looking at a substitution reaction that says that, oh, this must be this mechanism. We've got to look at the whole picture altogether. The last thing that we need to look at is whether there is an acid and base present. I put these over here as part of the environment, but in reality, acid versus base is very much a deciding factor on what happens in what these do to either the nucleophile or the electrophile. So I can be very simplistic over here and say that acidic conditions are typically SN1, whereas using a strong base is typically SN2. That just gives like a bit of a broad overview. Why do I mention something like that? Well, let's just look at a simple example of a tertiary butanol reacting with some kind of primary alcohol under acidic conditions. So we've got an acid present. So acid is typically like that. Right. So if we look at something, at a reaction that looks like this, at first glance, it's going to be a little bit sort of complicated, because we're going to say, okay, well, where is our nucleophile and where is our leaving group or electrophile? So when we look at this, we can see, okay, we've got basically two nucleophiles. Now this ends up being a problem. So when we look at our SCENE, our first thing is in terms of the electrophile, and looking at the sterics and the carbocation and that sort of thing of the electrophile, the first problem that we have is that we're stuck because there is no leaving group and it doesn't look like there's any electrophile present. The next thing that we need to look at is the nucleophile, and well, we've got two nucleophiles and both of them are alcohols. And so the nucleophile is certainly pushing towards, on the top, an SN1 type of reaction. But we can't see any reaction until we look at the environment. We're not told anything about temperature. We're not told anything about solvent, other than at the moment, it's likely, because this is an alcohol, that we might be in a polar protic type of solvent. Certainly we've got acid present, so there's protons. So the environment from a solvent side is probably leading, but we don't have that proper information. We don't have temperature, which would have been maybe helpful for me to have given in this reaction. We don't have that. But the environment does have an acid present. An acid typically says that we're going to SN1. Why is that? Well, an acid can protonate either one of those alcohols. And when it protonates either one of those alcohols, we change it into OH2 plus into hydronium. We change the alcohol into a good leaving group. In doing so, of these two that we have over there, if we change this one into an OH2, so we protonate that, we make something where we're going to get, if it leaves, a tertiary carbocation, which is sterically bulky. If this is changed into a good leaving group, this primary alcohol over here, we're going to get a primary carbocation that gets formed. And that is absolutely terrible. It's not going to happen, all right? It will not happen. So the only option in this reaction over here is that we need to protonate. For anything to happen, we're going to protonate the tertiary butanol. And the key here is, once that has happened, we have generated now a reasonable leaving group, because it's on that tertiary center. So from a steric point of view, we're going SN1. Carbocation is absolutely fine. It's forming a tertiary carbocation, so we can give it a double tick. The electrophile is totally fine now, as for that point of view. Nucleophile is there. The environment, because it was under acid conditions, says that this thing is going SN1. And so This can leave, we get a tertiary carbocation being formed, and now the alcohol that was the primary alcohol that is there can now act as our nucleophile. Very rapidly, it's going to want to react with that carbocation over there to form a new bond. And we're going to get a tertiary butyl ether being formed over there. Of course, we still have a proton left after that reaction, and the proton does need to leave. The proton can just leave because it is an acid, and so it can carry on and regenerate the acid that was we got in the first place. All right, so acid conditions typically lead us towards, because the acid is usually protonating an alcohol, it is something that typically leads us towards an SN1 reaction. Base is something that leads us towards an SN2, but we do need to look at it in the context of the reaction. And I go back to my original example at the beginning of this lecture, and that is when we looked at this one over here, we saw that the base that we had, sodium hydride, was a good strong base, which is going to activate the nucleophile. So we had a very bad nucleophile. It's a strong base. Over here, the environment is absolutely adding towards the fact that this is going to be a substitution reaction, which is SN2. Whereas this reaction over here, the base that's being used is not strong enough to activate the nucleophile. And so the environment is not pushing towards an SN2 over there. In fact, because that base is not doing anything to the nucleophile, it's basically pushing again that this is probably more likely to be an SN1 reaction. And that's that. In the next lecture, we will go through a number of examples, pretty much like what we've done now, but just to explore how we use this term and look at different reactions in terms of their mechanisms.